In this video, we're going to talk about what we call quadratic area and perimeter. And this is a nice application of the quadratic function. So there's a couple of things that are our goal in this particular video is to show how to maximize area through rectangles. All right, and so we know that in a rectangle, there's a couple things you need to know. You need to know for a rectangle, the area formula and also the perimeter formula. All right, and we're going to call the area for the area. We're going to label the rectangle I have here with a length that we'll call L and a width that we call W. And the area of this rectangle is just equal to the length times the width. And the perimeter of the rectangle is equal to, well, when we find perimeter, we add up all the sides, so we get 2L plus 2W. And quadratics are just rectangles. Literally, is what they are. That's why they're called squares. That's why you start seeing the exponent of the square there. So we're going to figure out a way to use this to make a square. And it's generally going to come from the area formula because you're multiplying two things. So we have an example here that says a piece of wire is 100 centimeters in length is to be bent into a rectangle. Let W be the width of the rectangle. So here's the key thing. We're defining a variable right here. We're defining the variable W as the width of the rectangle. So when we draw our rectangle here, here's what we know already. We know we have the variable W. And from this, we want to write an expression for the area of the rectangle. What are the dimensions which will give the maximum area? And at what width does the maximum occur? And what is the maximum area? So to do this, we know that we have this variable W already, right? And because of that, we know what they've given us, this 100 centimeters in length. That's what you're bending the wire into a rectangle from. That's going to be your perimeter. So we know our perimeter already. We know P is equal to 100. And here's what we know. We know if this is W right here, then this is also W over here. So what we have to do now is try to figure out a way to write the length up here and the length right here in terms of W. Well, you can see from this, if this is W and that's W, you've already taken up 2W from the 100. And that means that the length then, in terms of W, so I'll write it like this. I'll show you what I mean. The length is equal to, take up what you have, your 100, and you're going to take away from that 2W. And that's how much you have for the length on both sides. We actually need to cut that in half. This is going to have to be cut in half. So the true length, when you get this, if you cut 100 in half, you get 50. You cut 2W in half, you get just W. 50 minus W. So what we have here is this side is 50 minus W, and this side is 50 minus W. They're the same length. And what you've done now, if you've created the dimensions, you can see your dimensions. You know your length, which you're expressing in terms of W, is 50 minus W, and you know your width is just W. Now, I can show you how I got this using this formula, 2L plus 2W, right? And here's what we know. We know this perimeter is 100, and that is equal to the 2L plus 2W. Well, if I want to get an equation for W, I want to get W, an equation for W, what I have to do now is I need to move things around. I need to start solving for different variables. And in terms, I want to write L in terms of W. So that means I need to get L by itself. Because when I get L by itself, I'll have an equation with a W in it for L. And the goal is to replace that equation for L with something with W. So to get L by itself, I'm going to subtract off the 2W on both sides. So I'll subtract 2W from both sides. And here's what I get. I'm left with 100 minus 2W is equal to 2L. And the last step now is to get L by itself, so I'll divide both sides by 2. And when I do that, if I do 100 divided by 2, I get 50 minus 2W, or 2W divided by 2 is just W, minus W is equal to L. So this is how I do it for the formula. And again, I've solved the equation for L because I wanted an equation that had a W in it. So now I have a W here, and I can re-express L in terms of W. So now that I have this rectangle drawn out and everything's written in terms of W, I'm going to use the other information that I know. In particular, I'm going to use the fact that the area is equal to the length times the width. But remember, we're re-expressing our length here. We're re-expressing that in terms of W. So that's going to be re-expressed like this right here. So when we plug in, we get A is equal to the length, which is 50 minus W, times the width, which is just W. And by doing that, I can now distribute the W to both terms. So here and here. And when I do that, here's what happens. I get A is equal to 50W minus W squared. And this right here is where we get our quadratic from. Because now we have this quadratic term. Now from here, I can just use this equation that I've created to find the maximum value of this. And I know it has a maximum because this right here is the A value, and my A is negative. So I'm going to get a maximum here. And remember how we do this. Let's rewrite this equation where the A comes first. So now we're looking at the equation. A is equal to negative W squared plus 50W. And remember to find the maximum. We look at this right here. The maximum occurs at when X is equal to negative B over 2 times A. And the maximum value occurs when we evaluate negative B over 2 times A into the function. So what we're going to do is we're going to find negative B over 2A and then evaluate whatever that number is back into that function. And so here my A is equal to negative 1 and my B is equal to positive 50. So to get the X coordinate, I'm going to be negative 50 over 2 times negative 1. And that'll be negative 50 over negative 2, or just 25. So the maximum width, or the width that's going to produce my maximum, is when this right here is 25. And then I can also find the maximum length as well, which is 50 minus W. In that case, it'll just be 50 minus 25, or also 25. So all I did was I plugged in 25 for W here and got that one. And then I plugged in 25 here and did 50 minus 25 and got 25. And notice this, we have the same length and width. And that's because in general, anytime we want to maximize a rectangle, it will always be a square. A square maximizes rectangles. Henceforth, why we use the quadratic as a square. So I know the max occurs at 25. So when the maximum width is 25, so when your max width is 25, what is the actual maximum area going to be? All that is now is plugging into the formula and evaluate f of 25. And that'll be 50 times 25 minus 25 squared. And so when I do this, I get 50 times 25, which is 1250, minus 25 squared, which is 625. And then 1250 minus 625 is just 625. So the maximum occurs at 25, and that actual maximum area is going to be 625. And notice I worked this problem out. What I really could have done, though, is come back up to this rectangle. I know the width is 25. The length is 25. Area is equal to length times width. So that's just 25 times 25, which will also give me 625. So again, when we do this, though, I know that the maximum width is going to occur at 25. That actual maximum area is going to be 625.